Hey guys, in this video, I just want to briefly go over the difference between chiral, achiral, and meso, and just talk about a little bit about optically active and which molecules will be optically active, as well as like a racemic mixture and if that's optically active. So just to kind of begin, I just want to very briefly go over what each of these kind of terms are, because that is really important, because if you have kind of the wrong definition, it's going to lead you down kind of the wrong path. So if something is chiral, then that means that we have no sigma planes, no symmetry planes. I think that a lot of students get this mixed up because they see chiral centers, so they automatically think that it's a chiral molecule. Whereas in reality, it's really just if something doesn't have a symmetry plane, then it's chiral. And if it does, then it's achiral. So again, achiral is something that has a symmetry plane, but then what is meso? So meso is a subset of achiral. And so something that is, or everything that's meso is achiral, but not everything that's achiral is meso. So meso is there's sigma present, but there's also chiral centers. So again, just because you see chiral centers, don't necessarily think that it is going to be chiral. So, and then optically active. So chiral molecules are optically active and achiral molecules are not. And so if we have something that's achiral, again, it won't be optically active, but that also means that if we have something meso, then it won't be optically active, because again, meso is a subset of achiral. And so racemic mixture is just kind of a 50-50 split of enantiomers. And so if we have a flask that, let's just say, has 100 molecules of this and 100 molecules of this, if we shine light through it, it's not going to bend the light at all, because when we have chiral molecules, they bend it one way and then the enantiomer will bend it the other way. So all of the bending that this molecule has done basically gets reversed by this. And then I have quite a bit of examples, and I just kind of made these. So hopefully there aren't any problems, but I'm human, so I am prone to making errors. But I'm going to try to go through these pretty briefly, but still kind of talking through and drawing out the sigma planes that I see. So with this first example, this has a chiral center if you look at it and not really think about it. So if we draw in this hydrogen and then we say, okay, what is a chiral center? An sp3 carbon that has 4 unique substituents. If we go in to check, does it have 4 unique substituents? We go 1, 2, 3. And then if we kind of take a different path, 1, 2, 3, along the orange and pink paths, nothing has changed. Therefore, they're basically the same substituent. So even if, it's in a ring, you still kind of count each direction its own kind of branch. And I know that that was kind of confusing for me at the beginning, but you have to kind of go through each way. So this is actually not a super accurate picture. It should more so be like this, because that's not a chiral center. So it doesn't really have that chirality. And so hopefully now you guys can definitely see that sigma plane. It's like this. And so this would be achiral. But this would not be meso because it doesn't have any chiral centers. So for this next one, both of these are chiral centers, because if we kind of do the path checking, 1, 2, 1, 2, we notice that with the pink path, we encounter a chlorine. So they are chiral centers, but there is a sigma plane. So it's right here. And so that makes this meso. And so hopefully you guys can see that with the next molecule, basically it's the same thing, and it's meso. But you guys should also recognize that these two molecules right here are the exact same molecule. It's just pancake flipped. So that's why I put that one in there. And it also may be important to note that with meso molecules, the enantiomer of that is the exact same as the initial. So I should have maybe mentioned that before, but if you draw the enantiomer, it is just going to be the exact same. So if we draw this, It's the same molecule. It's just the chlorines were pointed into the board, and then we just changed our perspective. So don't get tricked up on that. Like if it asks for the enantiomer of a meso, it's just identical. All right. So in this case, we have a chiral center. And so now if we want to look, is there a plane of symmetry? And the answer is no, because if we kind of draw it, it's kind of hard to show, but if we were to draw it in the same plane as the paper, we would have a bromine on the left, but a hydrogen on the right. That's not symmetrical. If we were to draw it maybe like here, that's obviously not symmetrical. I mean, there's two different groups. So this one is chiral. Again, not because there's a chiral center, but because there's no sigma plane. So this next molecule, there doesn't look like there's a sigma plane to me. We have chiral centers, therefore it's chiral. Again, with this next one, if we were to draw in the plane of the board, hopefully you guys can visualize that there's a bromine on the left at this carbon and a hydrogen on the right. There is no symmetry. I did not do a very good job of kind of separating these questions. But so for this molecule, doesn't really look like there's a sigma plane, but we need to remember that when we are looking for symmetry, we want to look for symmetry in the most symmetric form. And so that may not make a whole lot of sense, but it's like looking for something in the most probable place that it's going to be. You're not going to look for kitchen utensils in the bathroom. You're going to look for kitchen utensils in the kitchen. And so we want to evaluate if there's symmetry in the most symmetric form. And so it may not make a lot of sense right now how we're going to make it in the most symmetric form. But as you do more practice problems, you should be able to just start rotating these and saying, okay, this looks like there could be symmetry. Let me rotate and see if there actually is. And so when we rotate about this carbon bond, we're basically taking all of the groups and we're just turning it. So we're leaving this hand alone. We're just turning this carbon. And so that is going to look like something like this. And so hopefully now you guys can see the sigma plane right there. And so again, chiral centers, sigma plane, it's going to be meso. Just as kind of a remark, I think that this is one of the most kind of freebie point that people miss because they just don't really look at it in its most symmetrical point. And I would say, I don't have access to the exams, but I have access to like the practice exams that you guys do. And the pattern that I have seen is that they almost always ask some sort of question like this, where you have to rotate to find out that it's meso. So this is definitely a good skill to have because your molecule may be a lot more intense than this one, but you still just have to rotate, look at it in its most symmetric form, and then go from there. So actually, I'm going to do this one next. So if we were to kind of look at it in its most symmetric form, quote unquote, we would get this. There's no sigma plane. There's chiral centers. Actually, the fact that there's chiral centers really doesn't matter, but we can go ahead and say that that is a chiral molecule. And then, so now we get to Fisher projections. And honestly, I find that Fisher and the Newman projections are a lot easier to determine if there's a sigma plane because it's almost kind of like set up in its most symmetric form. So with this first example, we can see that there is a sigma plane right here. And now we need to ask ourselves, are there chiral centers? And the answer to that is yes, right here and right here. These are both chiral centers, therefore it's meso. I don't want to say as like a blanket rule, but when you're given Fisher projections, normally these carbons right here are chiral. Again, that's not like a 100%. You still need to check, but normally they're chiral. And so now with this next example, if we were to go ahead and draw the same sigma plane, we can see that this group and this group are not the same. Therefore, there is no sigma plane. So it is chiral. And then with this example, this is kind of hard to see a little bit, but the sigma plane is basically in the exact same plane as the paper. So if we were to put the molecule in front of us and then we were to rotate our perspective, we're looking at it head on, there is a line of symmetry directly down the molecule. Now, I think that at least for me, I kind of struggled because it may sound dumb, but when we have O isn't really like a super good example, but if we have something like a chlorine, I used to, again, this may just be me, but I used to like not want to put a symmetry plane here because there's a C and an L. And we need to remember that these are kind of spherical molecules. So it's going to be something like this ball that represents chlorine. So it's going to be something like that. And now we can see that there is a sigma plane. And again, that may not apply to you, but for me, I found it a little difficult to do it with like a chlorine or a fluorine, just because like the letters themselves were not symmetrical, but just don't get messed up with that. So this molecule right here has a sigma plane, no chiral centers, so it's going to be achiral. And then again, another Fisher projection. So, if we go ahead and we draw this, again, the groups on the top and the bottom are not the same. But, and this kind of goes to what I was saying, it doesn't look symmetrical, but I believe that there is going to be a sigma plane right there. Because if we kind of treat these end groups as kind of just, again, like a spherical ball, I'm going to do them in different colors so that we don't get them confused. Something like that and something like this. So they're different, but there is still that symmetry on the left and the right. So don't necessarily say, again, with the letters, you don't want to say, well, the letters aren't symmetrical, so the groups aren't. You need to remember that these are representing kind of spherical molecules. So again, this one would be, actually, I think this one would be achiral, because in this case, these are not chiral centers. I just kind of made that example up, so it may not be the best one. So if that didn't make a whole lot of sense, I wouldn't worry about it too much, but I did think it was kind of a good one to note. And so now we get to Newman projections. And so you may want to say, hey, there is a line of symmetry right here because we're kind of going through two chlorines and we have these two hydrogens. But I don't think that these CH3 groups would be kind of working in the same symmetry plane. I don't know if there's an example like that. Actually, give me 1 second. All right, so I did just check and I was actually wrong. So just erase that from your memory. I think that in this case, it would be kind of nice to double check with drawing it out in line angle and then maybe rotating or doing something like that to verify. So I would go ahead and do that. And so when we draw out the line angle, let's make this our viewpoint. So we have a chlorine on the right on the front carbon and then a chlorine on the left on the back carbon. And similar with the alcohol, we can rotate and there lies the plane of symmetry. So try to, with the Newmans and the Fishers, if you're not super comfortable and you're more comfortable in line angle, convert to line angle so that you don't kind of make that mistake. And then in this case, let's again convert to line angle. So on the front carbon, we have a chlorine on the right. And then on the back one, we also have a chlorine on the right. So again, if we were to kind of go back to our alcohol examples, we know that this one is chiral because there is no sigma plane. And again, this one would be meso. So yeah, I feel like with Newman, it may be better to convert to line angle rather than trying to look for symmetry here. So now let's do this final example. So again, convert. So this one actually does not have any chiral centers. And there would be, again, a plane of symmetry basically cutting the molecule in half. So we're looking at the molecule in front of us, we change our perspective, and then we cut the molecule in half, and it's the same on both sides. So this one doesn't have any chiral centers and a sigma plane, therefore it's achiral. So these are just a few examples, and hopefully, again, I didn't make any mistakes. But now if we kind of want to go through and say whether it's optically active or not, again, we would just say chirals are active, achiral, and therefore meso are optically inactive. So, first, second, third, inactive. This one, active, yada, yada, yada. That is kind of this whole assigning whether it's chiral, achiral will be important when we get to the reactions. So make sure that you guys understand this. And I think honestly, the most important thing is just starting to recognize how to view these molecules in 3D. And that's kind of what this whole thing is about, because we need to kind of view them interacting with each other in 3D in chapters or units 3 and 4, because there's kind of geometric things and trends that we see. And so we need to be familiar and comfortable with kind of viewing these things in 3D and how they would rotate and, flip and this, that, and the other. So questions like this, I would say high likelihood that they end up on the exam, and they're not too bad as long as you do practice, because there are kind of little things and little tricks that you can use. So definitely with this unit and the introduction to chirality and stereoisomerism, that is where practice is, I think, kind of super duper beneficial. In unit 1, it was pretty beneficial, but here it's super beneficial because the more you practice, the more this kind of becomes second nature and viewing these molecules in 3D. So enough of my little rant. But if you have any other questions, again, like always, post on Piazza or group me, and someone will try to help you out. But good luck.